this video I'm going to be demonstrating how to drill a bolt hole circle or a series of holes on a pitch circle diameter. It's very common in engineering to have holes spaced out in a circular pattern, various numbers of holes depending on the application. A very common one to think about is a car wheel. The car wheel is fixed onto the hook using bolts through the holes in the wheel. The holes in the wheel are arranged in a circular pattern central to the centre of the wheel. I'm going to demonstrate firstly on this component how to centralise the centre line of the spindle with the centre line of the workpiece. This is normally done using a dial test indicator, and the process is commonly known as clocking in or centralising. This is going to centralise the x-axis and the y-axis, as I said, so that the centre line of the spindle is in line with the centre line of the workpiece. Firstly, we need to arrange the dial test indicator clamped on with the magnetic base to the spindle, so it will spin in a full circle. You then need to move the table so that it's approximately central, and arrange the dial test indicator so it's in a suitable position to be able to register on all areas of the circle. I need to raise the table slightly so that the dial test indicator can reach the workpiece. And as you can see, when I lower the spindle, the dial test indicator registers on the outside diameter of the workpiece. I'll just lock the spindle in position. When I rotate the spindle, it can be seen that the needle moves. This means that the workpiece is not central to the centre line of the spindle, so that will need to be remedied. First of all, I'm going to take the dial test indicator round to the rear of the workpiece and zero the dial. I'll then bring the dial test indicator round to the opposite side. I need to notice how far the needle has moved and also in which direction the needle has moved. Once I've noted that, I need to move the table in the X direction approximately half of the distance the needle has moved. I then need to re-zero the dial and then rotate the dial indicator back round to the rear. As it can be seen, the difference between the position at the front and the position at the back is not a great deal. What I'll then do is rotate the indicator round to the right hand side and use the x-axis hand wheel to move the table so that the needle is approximately at zero. I can then now fine tune the positioning by zeroing the dial at the rear and bringing it back round to the front. Once again, I need to move the table in the y-axis so that I'm approximately halving the distance between the zero and the needle. having zeroed the dial, bring round to the side, and using the x-axis hand wheel, bring the needle to 0. This process is continued, gradually fine-tuning the positioning in the same method. As we can see, the 0 is the same front and back, and it is slightly off the 0 in the X direction, which I'll now correct, and can now be seen that there is less than 0.02 of a millimeter variation between the position of the needle in front, back and right hand side. The needle is definitely registering on the workpiece. That can be determined by gently moving the dial indicator. This means that the centre line of the spindle is now centralised with the centre line of the workpiece, and at that point the x-axis and the y-axis can be zeroed. In order to do drilling operations on the milling machine, we need to replace the milling cutter with a drill chuck. This is a standard drill chuck, 3-jaw, same type as would be found on any pedestal or pillar drill, and it's been mounted on a holder which matches the fitting in the spindle of the milling machine, and it can be fitted into the spindle in the same way as any other tool. For this example, I'm going to be drilling a hole pattern with 5 holes which are equally spaced. In other words, the distance between each hole is the same handle, and one of the holes is going to be at the top, which is 12 o'clock. When you're calculating positions for both holes, in other words polar coordinates, you use trigonometry as shown in the previous photograph of the whiteboard sketch which I did, and you need to know where the angles on the polar coordinate circle are. 3 o'clock equals 0 degrees, 12 o'clock equals 90 degrees, 9 o'clock equals 180 degrees, and 6 o'clock equals 240 degrees. So the circle goes from 0 round in an anti-clockwise direction to 360 degrees. I'm going to fit the centre drill in, and then move the table to the position for the first hole, which is 18 degrees from 0. The pitch circle diameter which I'm using is 70 millimeter pitch circle diameter, which means that the radius from the centre to each of the hole positions is half of the pitch circle diameter, which is 35 millimeters. I've made a note of the X and Y positions for the 5 different bolt hole positions on a piece of paper, which I'm going to use as a reference when I'm operating the machine. On a bolt hole pitch circle diameter, we have 4 different quadrants from 0. This quadrant would be X plus and Y plus. This quadrant is X minus and Y plus. This quadrant is X minus and Y minus. This quadrant is X plus and Y minus, as you'll see as we progress. The first hole position is X 33.29 and Y 10.82. I'm now going to move the machine to that position. Now that's in position, I can use the centre drill to centre drill the first hole. In order to drill a hole on the mill machine, this handle is used. The quill lock needs to be released so that the quill can move up and down. The handle can be repositioned by pulling it slightly out and then finding a suitable position for drilling depending on the length of the drill. First hole's been drilled. I can then move to position 2. And repeat the process. Continuing on until all of the positions have been set and drilled. Having centre drilled all the 5 hole positions, I've now fitted a 5mm diameter twist drill, which is the correct size for an M6 tap, because we're going to be tapping the holes M6. There's little point in moving the table from the position where it already is, because you're just giving yourself an extra movement which you don't need. It's already in the same position as it was when I drilled the 5th hole. So I'm going to start drilling operations from that position. I've set the depth guide on the quill so that when the drill is touching the top of the workpiece, the depth stop has 20mm of drilling to do. The depth stop will stop the drill from going any further when it reaches 20mm deep. Aluminium is relatively soft, so I can progress the drill down through the material quite quickly. It would take longer if it was a tougher material such as steel. Depth stop holds the drill in position at the bottom of the hole. I can then move to the next position. Having drilled all of the 5 positions with the 5mm diameter drill, I'm now going to use a countersink tool, 90-degree point, to put a chamfer or countersink at the top of each hole. This is good practice when you're tapping a hole, to put a small countersink in equal to the depth of the pitch of the thread, and that produces a neat edge to the tapped hole. I've set a depth guide or the depth stop so that the countersink will drill 1mm deep from where the edge of the tool begins to cut the edge of the hole. As we can see, there's a small chamfer on the edge of the hole. I've now fitted an M6 tap in the drill chuck. It's a M6 by 1.0 pitch tap, which is a standard metric coarse thread for 6mm. For this operation, the spindle needs to be free to spin by hand, so I'd have to put the high-low selector into its neutral position, which is going to allow me to freely spin the chuck by hand. I'm going to use a spray, which is tapping fluid, to spray a small amount of lubricant on each of the hole positions, which is going to lubricate the cutting action of the tap. What I then need to do is to bring the tap down until it touches the hole, keep a small amount of pressure on the handle, and I've made a small bar which fits in the hole into the hole in the side of the drill chuck, and maintaining a little bit of pressure on the handle, I'm going to begin turning the chuck. The tap will then begin to cut its way into the hole and beginning to produce the screw thread. It's not necessary to drill, it's not necessary to tap the full depth of the hole in this operation, because the workpiece can be taken away to the bench and the tapping completed to the full depth by hand using a tap wrench. Having done the first one, I'll then move to each of the remaining 4 positions and tap the holes. For this exercise, I used trigonometry to calculate the positions for the bolt holes in this exercise. If for any reason you're not able to calculate using trigonometry, you can go online and find a website which contains a bolt hole position calculator. This is used by inputting the pitch circle diameter, the number of holes, and the angle for the first hole relative to the 0 angle. The next couple of still images will show links to that website.